Hi, this is Jose Luis, and welcome to a new hands-on exercise on the series Introduction to Parametric Modeling. In this exercise, I would like to teach you how to model a parametric chessboard. And some of the things that we will be able to control in this model will be, for example, the size of the cells. It will be how many cells do we have in each direction, so in the X direction or the Y direction. Then how many rows of these pawns, for example, we can have in each direction, and of course the dimension of each one of these elements. This is going to be a good exercise to learn, for example, how to work with grids. It's also going to be a good exercise to learn some tricks about how to do things that look like data manipulation, but are not exactly data manipulation, are just working with the relationships of the size of elements in this grid, for example. And it's also going to be a good exercise to learn how to use temporary geometry, or geometry that is not going to go to the final model, just as a helper to find, for example, center points, or to find relations between elements. So as you see, the exercise is going to get fairly spaghetti-ish very soon, but actually everything that we're doing here is fairly simple. It's just cells, it's just deconstructing points, adding, doing simple arithmetic, and then creating planar surfaces here. So this is going to be a super interesting exercise, and if you're interested, follow me and let's take a look at how to do this. Let's get started. And as we typically do, the first thing that I would like to do is to take a closer look at what are we going to be doing here and plan a little bit ahead, the steps of how I'm going to approach the modeling of this exercise. So as we said, we're going to model a checkerboard or a chessboard, and probably the checkerboard looks something like this. It's going to be some kind of grid in 2 dimensions with lines, and then hopefully what we will do is that we will be able to control the size of the size of each one of these cells. So maybe we have the width and maybe we have the height of each one of the cells. We may also want to control how many of these cells are in the X direction and how many of these cells are present in the Y direction. So we know that typical chessboards have 8 by 8 cells, but this is parametric cell chess, so we want to make it as versatile and as flexible as possible. So this might be the number of cells in the X direction, and this might be the number of X in the Y direction. Okay, and then something that we might be able to do is once we have this, so this is going to be probably the first step, and it's going to be, I'm going to say that it's going to be the parameters that I'm going to choose. So the size of the cell and how many cells we have in each direction. After that, the second step will probably be doing something where we actually flag or we mark which one of the cells should be white and which one of the cells should be dark. And then the way we're going to do that is by simply having some of them be tiny square surfaces that are solid, if you will, and the other ones just having nothing on them so that we can differentiate them. And after that, we probably want to do something where we lay out either a grid of pawns or figures on both sides of the checkerboard. So for example, we can have 2 rows or n rows of elements on this side and I don't know, however many elements on the other side. Okay, or if we're going to go for the checker approach instead of chess, we can place like tiny cylinders like this on this side and on the other side. And of course, how many rows we have is also going to be parametrically defined, because why not? We are parametric people here. Okay, so I think those are going to be the main 3 steps, or in this case 4, the main 4 steps that I'm going to follow. First, I'm going to draw the grid on the screen, and it's going to be parametrically defined. Then second, I'm going to draw the solid checker cells, so which ones are solid and which ones are not. And then third, I'm going to place the elements on top of the chessboard. Those are going to be either pawns, 2 rows of pawns on each way, or 3 rows of checker tiles on each one of the sides. So for each one of the steps, we will go back to the diagram and we will break down the logics of how we're going to do that. Okay, let's take a look at how to do the first thing, the grid in Grasshopper. All right, so let's get busy. I'm going to do this manually, but I think for further videos, I'm just going to assume that you know how to create the parameters, etc. But for the time being, I'm still going to do the creation of all the input parameters manually. So the first thing that I'm going to do is I'm going to create some point in Rhino, and then I'm going to bring the point into Grasshopper the way I've taught you before already. And this is going to be the bottom left corner of the chess, so that I can move the chessboard in three-dimensional space, and I can have it anywhere that I want. Now, the other thing that I'm going to do, and so I'm going to add a couple sliders, and one is going to be the cell size, okay? And I think I said in the previous diagram that we were going to have two sizes, X and Y. We could have the cells not be square, but I think for the sake of simplicity, I'm just going to choose to have them be square. So I'm going to have one dimension, one value for both dimensions. And this is going to be, for example, the value of 1.5. Now, what I would like to define as well is cells in X direction. So how many do we have in the X direction? I'm going to right click here and make sure that it's a natural number, and this is somewhere between 0 and 8 and 20, and I'm going to set it to now the value of 8, for example, and this is going to be equal and cells in the Y direction. Okay, so I'm going to group this, and I'm going to call this my inputs, and this is what I'm going to start working with. Okay, so wonderful. So I think we're ready for this. So what is the first thing that we're going to do? Remember, the first thing that we're going to do is we're going to create the grid. So if I turn things off here, we're going to create the grid in 2 dimensions. So turns out that that is actually super easy to do in Grasshopper, because if we go to the vector category and if we go to grids, into the vector tab in the grid category, we actually have a lot of components that give us different ways of creating grids in Rhino. So that is, we can use hexagonal, radial, rectangular, whatever, or triangular. So for this one, I'm going to choose square, just because it's easier and it's closer to what I want to do with my checkerboard. So if I look at the inputs, you can see that the first is the plane for the grid, and I'm not going to be using planes yet because we haven't talked about this yet, but I'm going to plug in points, and I will explain why very soon, why points work when I plug them into planes. This is going to be the size of the grid cells, so I have this already here, and then the amount of grid cells in the X direction, so that's going to be this one, and this is going to be this one. So now I have a grid that I can move around by moving the point in Rhino, but I can also change how many elements I have in each direction. All right, so this is great. So this is going to be now, and this is going to be, for example, what is it going to be? This is going to be the grid. Okay, wonderful. So we got this ready. What is the next thing that we're going to do? Now we have to turn on and off alternative cells. The way we're going to do that is going to be a little bit special, because there's 2 ways we could go about this. One is, if we are here in our definition, you can see that the output is the outlines of the grid, which if you plug here a panel, you could see that they are rectangles. So each one of the cells is actually a rectangle. They're not continuous lines. And therefore, what I could do is I could just create a flat surface with the boundary being each one of these rectangles, and then therefore I can create solid square surfaces out of each one of these rectangles. And then after that, I could do a process where I could use data manipulation to turn on and off alternative squares in this grid. However, we haven't taken a look at data yet, so that approach is still a little too early in this series to be implemented. So what I'm going to do is I'm going to use a simple geometry trick. Okay, so we know how to create cells we know how to create grids we know how to create grids. And also something that we can do with grids is that the other output of the grid component gives us the points at the grid corners. And I can actually see those if I plug here an empty box of points and I plug those here. You can see that this grid as an output is also giving us the corner points of the grid. And if I were to use these corner points to create a primitive surface, like for example, a simple rectangle, where is a simple rectangle? Yes, here in primitive, a plane surface. So if I were to use this as for plane surfaces, you could see that I could plug all these points. And then if I make this a little smaller, so for example, this and this, you can see that I can very easily place rectangles in each one of these, in each one of these, in each one of these, in each one of these corners. Okay. So the idea here is that if I can do that, then maybe what I can do is I can actually create myself a grid that is a little bigger, that lives on top of my grid, on the previous grid that I've done, and use that as a baseline to create these plane surfaces. So that, and for example, if I make a grid that is this big and this big and this big and this big, or actually let me just draw this on the diagram. If I create a grid that has a point here, another point here, another point here, another point here, 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 all of these points, then you see how I can create rectangles that are going to live here, 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 etc., etc., etc. So I can create half of the rectangles by just creating a grid that lives on top of that. And then if I start off from a grid that is based on this point, then I can create another grid with the same parameters and therefore have this point, this point, this point, this point, and then create this one, this one, this one, this one, etc., etc. So what I'm going to do is I'm going to try to create a grid that starts at the same original point here, and then it's something like this. It's a grid like this, like this, like this, like this, and like this. And then take each one of the corners of that grid and use it as the base for drawing a rectangle. Okay? So let me try doing that. So I'm going to go back to Rhino, and then I'm going to delete this thing here. And then what I'm going to do is I'm going to create another square cell. So I'm going to turn this off first, and then I'm going to drop here another grid. Okay. And then I'm going to use the same base point for this grid. Now, keep in mind that we said that the grid that I'm going to create now is twice as big as the first one. So what I'm going to do is I have to say that the cell size must be multiplied by 2. And at this point, I'm actually going to use an expression just because I like them better. All right. And then this is going to be 2 times x. And then I'm going to plug in here. And then this is going to be the value that I'm going to place here. And you can see how, this grid now is like twice the size as the first one. But the problem is that the amount of the amount of cells is a little larger than what I want. So what I want probably is half the amount of these elements. So for example, if I do amount in the x direction, so that should be x divided by 2. And I'm going to plug this in here, and then I'm going to say this is going to be x divided by 2 as well. And now I have this grid here that is a little larger. So if I now use this as the base for drawing my simple primitive, so my plane surface, then I can have these points as the base, and then the size is going to be the cell size in the X direction and the cell size in the Y direction. Yoo-hoo! All right. This is almost great because we have the cell, this is the cell, original grid, and this is the cells that we are turning on and off. The problem is that this is not exactly right because here I only want 4 elements and here I have 5 elements just because I have that many corners, correct? So what I need to do is I need to figure out an operation here that tells me given 8 numbers, given 8 cells, it gives me the amount of cells, the amount of cells minus 1. So what is that going to look like? So what we're going to do here is we're going to use a small mathematical trick. So right now, whenever I have 8 cells, what I want is the amount of squares in the X direction to be 3, because I want the grid to overlay the way I have here in the diagram. So if I have 8 cells in the X direction, if I have X cells in this, if I have 8 cells in the X direction, I want 3 cells in the grid that I'm overlaying. So the way I can do that is, first of all, I can say, well, I would like the number of cells in the X direction to be X minus 1. So for whenever I get the value of 8, now this is going to be 7 divided by 2. And the result of that is going to be 3.5. But the idea is that I don't want 3.5, because then this component is going to take that number and is going to round it up to 4, as I can see here. So what I want to make sure is that the result of this division is always going to be rounded down. Rounding down in mathematical terms is equal to an operation that is called floor. If you see here, floor is going to return the largest integer that is less than the specified number. So for 3.9, it will return 3. For 3.2, it will also return 3. It is the opposite to another operation that is called ceiling, which is basically rounding up. And then it's also different than another operation that is called round, which is round always snaps to the integer that is closest, whereas ceiling rounds up and floor rounds down. So what I'm going to do is I'm going to use floor to round to the nearest integer down. So what I'm going to say is I want to calculate the floor of all this operation here. So that's going to be X minus 1 divided by 2. Okay? And so that what that means is that when this is 8, the result of this is going to be 3. But when this is 9, the result of this is going to be 4, which is something that I actually want. And when this is 10, it's going to stay at 4. When this is, you see how the grid is growing correctly? All right, and then I think here that for this one, I want to use the exact same technique. So floor of X minus 1 divided by 2. And then these white spaces, I'm just doing them for decoration. And then here, now I have for each, oh, no, what is going on? If I grow in this direction, oh, sorry, because I have to plug this one here. So if I grow in this direction, there you go. And if I grow in this direction, there you go. Wonderful. So it's working. So now I have the first, and remember, this is just an overlay that I'm using temporarily to use the points that are generated in that grid as the baseline for these rectangles that I am drawing as plane surfaces. The only thing that I need to do now is I need to do the exact same thing, but instead of just for that layer, what I need to do is I need to do the same thing for another layer, which is going to be starting from this point here. I'm going to create this grid here, here and here, and here and here. And then I'm going to create all of these points. And then I'm going to be able to use those points to create this, 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 and then this, and this, and this, and this, etc., etc. You get what I'm going with this, okay? Whoa. All right. So then let's just do that. The only thing that we will need to do is we will need to use the exact same technique that we have used, but the difference will be that before I need to calculate where this new point, the new base point is, which is very simple. It's just whatever this point is and plus x and y, the size of the cell. So let's do that. So I'm going to take this point here. I'm going to take this point, and this is going to be, let's start wrapping things up here. So this is going to be first set of cells. And then I'm going to take this point, I'm going to deconstruct the point, and I'm going to take the x and y and z coordinates, and then to the x, I'm going to add the size of the cell, and then to the y, I'm also going to add the size of the cell, and then I'm going to construct another point with the new x and y. So the x is the same one with the cell size, etc., etc. And this is going to be this one. So you can see how now I have this new point, which is the base for my grid in each direction. And now what I need to do is I can maybe copy paste this whole thing, just move it here. I'm going to ungroup it. And then, oh, you can see how I'm starting to get a lot of spaghetti. I'm starting to get a lot of wires overlays. So we're going to take this point and we're going to plug it at here. And then now we have the size, and this is working for 8, but it may not work for 9. Exactly, it doesn't work because it goes 1 unit too far away. This is because in this case, I need to, the rounding is not working. So I need to change the rules for the rounding in this case. The only thing that I need to do here now is go into my rules and then saying that the floor, instead of subtracting 1 unit, we're going to subtract 2 units so that the number of cells is 2 units less before we divide it and we round it down. Is this going to work? Let's see. So these are the new squares. So if I make them 10, now I think it's snapping to the grid very nicely. And if I do this in this direction, it's also snapping to the grid very nicely. So I think we are good. So this would be the first set of cells, and this is going to be the second set of cells. Again, we could have done this in a different way by doing data manipulation, creating all of them, and then just removing them alternatively. But since we don't know how to do data yet, I chose to just use this simple trick here. Okay. Now I'm going to turn off the visualization of this grid and this other grid and just stick to the first set of cells and the second set of cells that we can see here. All right. Wonderful. I think we are ready now to take a look at how to create the pawns and the checker tiles to play with here. Okay, let's take a look at how to do that. Okay, so let's go back to the drawing diagram. So for this one, what we want to do is we want to be able to place some, we're going to do some simple cones just to represent like pawns, for example, as if this was a chess game, right? So the tiles, the pawns for a chess game. Now, what we're going to do here is that, very simply, we're going to apply the same trick that we did in order to find the location of the center of each one of these elements. So if you look closely here, we can see how the arrangement of the tiles in this direction, in this area, is something like this. I could actually draw a grid here, something like that. And each one of the corners of the grid can be the center of each one of these elements. So, and the rule is going to be very simple actually. So if I want to say that I want 2 rows of pawns, and I know that I have 8 cells in this direction, for example, then what we can do is we can say, I'm going to create a grid that starts at this point, and I know the location of this point is the location of the starting point here plus half the size of the cell. And then I can create a grid that is, if I have 8 cells in this direction, then it's going to be 7 cells, 1 less. And then if I want 2 rows of elements in that direction, then it can be just 1 cell in this direction. So I can create that grid and populate it with cones, and then I can do the same thing on the other side of the checkerboard. Let's take a look at how to do that. So let's do this. So I'm going to take the point, and again I'm going to deconstruct the point, all right? And then what I'm going to do is to the x, I'm going to write an expression here, and then what I'm going to do is to this x, I am going to, and this is going to be cell size. What I'm going to do is to whatever the x was, I'm going to add half of the cell size. And the cell size is going to be the parameter that is coming in here from here. All right. So my rule is going to be that whatever x was, take x and add half the cell size. And that's going to be the same also for the y direction. Remember that this x, the naming of this x, the fact that this is connected to this x has nothing to do. This could be whatever, I could call this coordinate. It doesn't really matter. It's just that I will need to change that also inside coordinate. So whatever the coordinate is, just add half of the cell size, and that's going to work for x, and it's going to work for y. And now I'm going to construct the point, and the point I'm going to construct it with the new x coordinate, with the new y coordinate, and the same z coordinate. All right. So you can see that the point, the first point for the grid, is now at the center of the first cell. And is this true? Let me just move things around. Yes, so this is true, and if I make this bigger and smaller, things are still working. Okay, this idea of like changing parameters and making sure that things are tight as we go is a very common thing. It's a very good thing to do. So now I have the base here, so now I can create a grid. And the grid, as we said, is going to be a square grid. Where is my square grid? Here. It's going to be a square grid. The size of the grid is going to be the cell size that I have here in my input parameters. And then what I need to make sure is that I do a little bit of numerical operations to make sure that the amount of cells in the x direction is right and the amount of cells in the y direction is also right. So what am I going to do? So if I plug in here amount of x in the x direction, you see that I have one more than I want. So what I need to do is just simply take that number and subtract 1. So I'm going to use an expression, and I'm going to say, whatever you give me, remove 1 unit from there. So what I'm going to do is I'm going to plug the number of cells in the x direction, and I'm going to plug this in here. So now in the x direction, I have the right amount of cells. So if I make this bigger and smaller, this overlay grid is working well in the x direction. And now, what about the y direction? Well, I actually don't have anywhere in my code, I don't have anywhere where how many rows of tiles do I want to have. So maybe I can add that as a parameter. So what I'm going to do is I'm going to create a new parameter here, which is going to be, I'm going to copy and paste this one, and it's going to be tiles in rows of tiles, for example. And I'm going to set this to the number 2, okay? And I'm going to set that the minimum may also have to be the number 2 always. The minimum may have to be the number 2 always. So I'm going to add this to group, and then remember that we said I'm going to copy and paste this, and I'm going to say whatever number of rows has to be that number of rows minus 1. Because remember from the diagram, if I have 2 rows, then I only want 1 cell in that direction. So I'm going to plug this in here, And now, yoo-hoo! And now I have an overlay grid that has point elements in the corners that I can use as the centers for some geometry that I can place on top of that. Wonderful. So now we can use this as the center for the tiles. So for example, I can just go to surfaces, primitives, and then I can place cones, for example, in each one of these centers. So the base is going to be the points, and woohoo! How is that? How cool is that? And then the radius and the cone height will be parameters. So maybe what we can do is we can either say that the radius, for example, has to be, I don't know, a factor of the cell size. So for example, and these are going to be parameters. So for example, I'm going to say rows of tiles, and then I'm going to write here, I'm going to copy this slider, and it's going to be tile size factor. And then I'm going to say that this has to be somewhere between 0 and 0.5. So that, for example, if I say the size has to have a radius that is 0.4 times the cell size, for example. Or I could just do this numerically. So for example, I can just say tile radius, and that's going to be, for example, 0.4 in this case. And then I can just plug that in here, and then this can be the radius of the cones. And then I can also say tile height, and then I can crank that up a little bit, and then plug that in here, and then that's going to be the length of the cones, for example. All right, and I can now turn off the point, I can turn off the grid, I can turn off the points, and now you can see how the cones are now, they are now much nicer. But one thing that I don't like about having the tile radius be a hard-coded number is that if for some reason I was redesigning my board and then I made the cell size much larger, then you see how the tiles are just like, they stay with the same absolute number, absolute value. I kind of don't like that. So I may want to choose that the size of the radius might have to be a factor of the size of the cell, maybe. If depending on what I'm using this for. Is this for visualization? Is this for fabrication? If it is for fabrication, maybe I'm actually interested in the real world size of the pawn as opposed to a factor. So ultimately, this is up to you. What kind of factors or what kind of numerical relationships do you establish? Okay. All right. So so that's one thing. The other thing now is that we need to create the other grid. So we need to create the second grid, a grid that is going to be a grid that is going to start on this point here, and then is going to be something like this. And the only challenge here is going to be to find where this point lies here. And the trick here is going to be that we're going to say, for example, that the location of this point is going to be the same as the location of this one here. But in the y direction, what we need to do is we need to add an amount of cells, which is equal to how many cells do we have in the total direction minus the amount of cells that we have, the amount of rows that we have for tiles. Does that make sense? Because if we have 3 rows, this point would be here. If we have 4 rows, this point would be here. So it needs to be the amount of total rows in one direction minus the amount of rows in that of rows of tiles. I'm not explaining myself very cleanly today, huh? This is getting a little messy. So let's give it a try. Let's see how we could do that. So I'm going to go back here, and I'm going to take here and group this and say first set of pawns, for example. That's going to be 1. And then I'm going to take the point that I created here, and I'm going to deconstruct that point. So I'm going to deconstruct the coordinates of that point, and then I'm going to create a new point that has to be somewhere here, and the coordinates of that point are going to be, I'm going to construct a new point. The x coordinate is going to be the same. The z coordinate is going to be the same. But now the y coordinate has to be the amount of rows in this direction, the amount of cells in this direction, minus the amount of rows, multiplied by the cell size. So let's see if we can create an expression to help with that. So I'm going to create an expression, and I'm going to say cells in the y direction. That's going to be one of the inputs, cells in the y direction. The other one is going to be cell size, and the third one is going to be rows, tile rows. So how many rows do we have in each direction? How many tiles do we have in each row? So I'm going to move this here, and I'm saying this is the amount of cells in the y direction. This is the size of the cells. And this is how many rows we have in each direction. So now I have the 3 numbers plugged in. And then here I'm going to write the rule, which is going to be how many cells do I have in the y direction minus how many tiles do we have per row. And all of this needs to be multiplied by the cell size. So cell size multiplied by this minus this. You see why the expression component, I like it so much, because doing this with components like plus and minus whatever is actually a little tedious. So let me do that, and then, and let me actually plug the y the y value. So I'm going to add the y value here, and then this is going to be whatever it was before, plus all this stuff that I just calculated here. So this y plus cell size times blah, blah, blah. Oh, all right, this worked. So you see how this point is now here? Let's mess a little bit with the inputs to see if things work correctly. If I change the cell side, it sticks. If I change the amount of cells in the y direction, it sticks. And if I change the amount of rows, it also comes back down. So this is looking really neat to me. Oh, so I think after that, the only thing that I need to do is, given this point, I need to create an overlay grid, which is exactly the same as the previous one. So the previous one was all this stuff here. So I think I can just copy paste all of this. And then the only thing that I need to replace is the point that I was using as the base here. And let me turn this on. So I have now created that overlay grid, and I have placed a bunch of cones on top of them. And I think I am done then. So let me turn this off. So you see the base point, the grid, and then each one of the cones that I have placed on top of these, the points of that grid. Woohoo! And does this work? So I want more row, more tiles. If I make this larger in this direction, if I make it bigger in this direction, oh, everything looks really, really parametric to me. This is awesome. Alrighty, so this is looking great. So then I'm going to this second set of pawns. All right. So I think with this, we have kind of finished creating a parametric chessboard of sorts. I have my cones here and I have my other cones here. So this is looking pretty neat. I'm going to turn off this point so that it's not very visible. And all right, so this is our parametric chessboard. Now what I'm going to do in this video is I'm going to continue, and I'm going to add a little bit more of components, so that instead of just the rows of pounds, we can also have rows of checkers. And this is going to involve doing, like, again, this trick of like the grids, etc., etc. So it's going to take me some time, so stay tuned on this video if you want to see how I do that. Otherwise, just jump on to the next video. You think you're good with this already, okay? All right, and I'm actually going to apologize, but I'm just recording more of the videos in this series, so I kind of want to move on to other videos. So remember when I said I was going to do the checkers? So I'm kind of not going to do them. Sorry. But instead, what I would like to just say is I would like to open it up to you, the viewer, if you want to try this exercise on your own. And the way it could be done is actually very simple. So we can just use the same technique to say, well, I'm going to first create a grid that looks something like this. It's twice as big as the cell size, and then the first point is going to be here, which we know is the original point plus half the cell size, and then I'm going to create all those points here with the grid and use those as the base for the checkerboard. And then I could create similarly another grid here, and then figure out where this point is given the location of this point, and I can do that a little arithmetic to find that. And you can also say that for this one you can create another grid of points here, and you cannot create a grid with 0 rows. So for this you would have to have at least 2 rows of elements, and here you would have to have at least 2 rows of elements. But you can also create another grid here that completes that. So at the end of the day, the only thing you have to do is you have to create 4 grids for each one of them, figure out the starting point parametrically, working with the relations of how many rows you have, and then use those as an overlay to find the corner points and place the tiny tiles for your checkers. If you're watching this video and you want to give this a try and you complete the exercise, extending the exercise that we did here, feel free to post a link to that file on the comments of this video. And if you like, and if you give us permission, we will add that file to the repository where we keep the sample files that we do here, and so that other people can look at your code and learn from it. Okay. All right. So sorry for that, but I want to keep recording other videos. So thank you. If you like what you saw, make sure you subscribe, you like this video, etc. And this video was part of the series Introduction to Parametric Modeling. We are doing a hands-on exercises to practice what we've learned in the main playlist. And I'm going to keep on doing more of these exercises in the forthcoming videos before we go back to new content. Okay? Thanks a lot, and see you on the next video.